All right, we're going to go ahead and get started. I want to say hello and thank you for joining us. Today, senior scientist Maxime Lemurdy will describe the use of a PBPK approach for the drug development and demonstrate the ability to predict differences in PK in pregnant subjects. A few housekeeping notes before we begin. We take your privacy rights seriously. By attending this event or participating in the Q&A session, you're allowing us to contact you for follow-up. You may ask questions via the questions panel on your dashboard at any time. If you need assistance, please use the hand raise icon. So before we begin, we want to go ahead and launch a poll. And the first question is, are you currently using GastroPlus? I'll give everybody a few more seconds on the poll. All right, so it looks like most of you aren't, so hopefully you get to learn a little bit, and maybe you will in the future. So about today's presenter, prior to SLP, Maxime Lemurdy joined the FDA in 2017 as a postdoc fellow in the Division of Quantitative Method and Modeling within the Office of Generic Drugs, where he developed his expertise in PBPK models for locally acting drug products and published multiple papers on ocular delivery models. Prior to this experience, he published on a biomarker of alcohol consumption as well as the physiological modification affecting children's pharmacokinetics. Take it away, Maxime.
Thank you, Jasmine, and thanks to all of you for joining this webinar today. Based on the poll, I see that roughly 60% of you are not super familiar with GastroPlus. So as I will go over the case study, I will also introduce the software briefly and how it's basically set up. But today, the goal is to talk about how we do PBPK models for pregnant subjects, but also how we are able to predict how the drug goes from the mom to the fetus at different stages of pregnancy. So I mentioned different stages of pregnancy because, as we know, so the pregnancy lasts for 9 months. They are typically divided into the first, second, and third trimesters. And from the mom side, the physiology evolves quite drastically as the pregnancy evolves, with change in body composition, change in their liver metabolic capability, and many other changes. So to be able to predict the PK differences from the maternal side, we need to account for all of those changes. But it's not all, because during those 9 months, there will be the embryonic development. And you can imagine that from a few cells after a few days to a full baby ready to be born after 9 months, there's going to be drastic differences in terms of physiology, in terms of flows, exchange between the mom and the fetus. So it's actually quite a complex mechanism that we need to focus on, and also a perpetuous evaluating mechanism during the course of the pregnancy. And we need to consider both the mom and the fetus, as they can both have impact on a compound pharmacokinetics. First, I'd like to take a step back and look into the different guidances that are out there for development of drugs considering pregnancy. The first guidance published in 2004 by the FDA was a guidance towards the industry entitled Pharmacokinetics in Pregnancy, and it was talking about study design, data analysis, and the impact on dosing and labeling. What is interesting to note in this guidance that is now almost 20 years old is that it's the first time they talk about PK modeling approaches directly into the guidance for pregnancy analysis. It was a population PK approach, so not what we're going to discuss about, but the word modeling was already there. In 2006 and 2009, the EMA echoed the FDA with two new guidance and guidelines. One talking about the exposure to medicinal product during pregnancy, and one to evaluate the risk assessment of medicinal product on human reproduction and lactation, going from initial data all the way to labeling. 3 years back now, the FDA published a new guidance entitled Pregnant Women, Scientific and Ethical Consideration for Inclusion in Clinical Trials, and that guidance was also directed towards the industry. And there's one sentence I really like into this guidance, which is PK studies, including pregnant patients, physical changes during and after pregnancy that are critical for drug absorption and disposition may need to be considered in the model. So when you read those words, physical changes that occurs during and after pregnancy that impact both drug absorption and disposition, that directly points towards the direction of PBPK models. And this is what we will talk more today. But first, let's look at how do we get clinical information actually for pregnant women. And there are two ways to get those data. The first way is to actually include a pregnant woman into a clinical trial. So this has an advantage. It's a very safe process. The pregnant woman goes to a facility, a research facility, an hospital. She can receive the drug in a controlled environment. And if there are some side effects, they can be detected very early on. And also the number of subjects that we need to identify the side effect is limited. However, those trials are doable only and if only the drug provides direct benefits to either the mom or the fetus. If there is not these direct benefits, it would be unethical to include those pregnant women into the clinical trial. Therefore, for many drugs, clinical trials are a very big challenge. And what is actually done are post-marketing studies where the drug in real life are simply given to the pregnant population or to pregnant women, and it's only after a certain time or after a side effect occurs in a large population that we can actually detect it through pharmacovigilance processes. And that really raises a case of safety concerns, because it means that only after a large number of patients will suffer a side effect that our system will be able to detect it. And obviously, there are some ethical limitations to take the risk to do those kinds of real trial live. So there is other approaches that are necessary, and one of them is to include PBPK models. But before we go further, I'd like to invite Jasmine to launch the second poll question. So the question is about, in your opinion, how many drugs a woman takes during the course of her pregnancy? And thank you, Jasmine. I think we can stop there. We start to see a trend. So a third of you thinks 4. Some of you thinks less. 23% of you thinks only 2. And that means that 50% of you thinks more than 4. The real answer is actually not a round number. It's 4.2 in average. And at least those are data from 2018. And that suggests that actually women will take 4 drugs during those 9 months. And in most cases for those drugs, we don't really know the real impact. And very interestingly, there is one drug for which we always consider to be safe to be used by all physicians and pharmacists during all of the stages of the pregnancy. It is paracetamol or acetaminophen. And even thinking in very large scales that paracetamol is a safe drug to be used, an article published last week in Nature Review raised a concern about using paracetamol during pregnancy, and it really made a call for precautionary actions. In their human observational studies, they've identified that potentially paracetamol could be linked with troubles happening at the perinatal age with increased genital malformations. It could be linked with personal development troubles during childhood, such as ADHD, autism, hyperactivity. And there could be an increase in early puberty onsets during adolescence and adulthood, which means that paracetamol, although we thought was a very safe and efficient work to be used during pregnancy to cure like some fever and some pain, maybe large concentrations or using it too often could be an issue. And in this paper, they recommend that acetaminophen or paracetamol should be used by pregnant women cautiously at the lowest effective dose for the shortest possible time. So basically what they say, don't use it unless you don't need it. And if you do, go very slow and for the shortest time. What they mention again is the long-term or high-dose use should be limited to indication as advised by the health professionals. So then we enter the risk-benefits assessment between a potential risk in the developing years of a child and a direct effect of the paracetamol. So that's really to raise the point of there is a need to develop more tools to assess how the drugs actually will distribute into the fetus body at different stages of pregnancy. Can we predict it? And how can we actually improve the safety of all of those drugs that we are putting on the market? And going back to that FDA definitions, as I mentioned, because I really love this sentence, physiological changes during and after pregnancy that are critical for drug absorption and disposition may need to be considered in the model. So going back to the definition of PBPK, PBPK stands for physiologically based pharmacokinetic models. So we have the physiologically part here, as we consider a lot of physical parameters, such as body composition, metabolization, enzyme expression level in different tissues, etc., etc. And what is possible to do with those models is to change those parameters and make them evolve at different stages of pregnancy to predict what would be the situation the drug would face when it's administered to a pregnant woman. So this is basically what we've done. And you can see on the slide here, the structure of the PBPK model as it is currently implemented in GastroPlus. So on the left-hand side here, you have the maternal side PBPK model, which is the typical PBPK models we have in GastroPlus, except we include two more tissues. We have the uterus right there, and we have one fraction of the placenta, which will be the maternal placenta. This PBPK model, although doesn't have the typical physiology of unhealthy subjects. Based on when you are in the pregnancy, for example, first, the weight of your subjects will evolve. And we have a relationship that links the weight gain during pregnancy to the gestational age. And that will impact the weight of some organs, but not all of them, because we know that some organs will increase in size as the pregnancy develops, but some of them won't. So we account for those changes in the model. We also account for physical changes that affect the renal, the gastrointestinal, or the cardiovascular systems by changing the blood flow, changing the renal fraction, the GFR. The body composition will also change as the pregnancy develops. So we have those equations included in the model. And finally, the metabolism, which for most phase 1, so the cytochromes, metabolic enzymes, we have relationships that express the enzyme level as a function of gestational age. So that's for the maternal side. On the right side, you can see how the fetal PBPK model is linked to the maternal with different pathways. And I will go back in a few slides on what they mean exactly. And then we have the fetal PBPK. So as I mentioned in the first slide, the fetus will evolve quite a lot between the first day of the pregnancy and the delivery. So we have nice relationships that are able to describe the body weight and the height of the fetus, once again, as a function of gestational age. But it's not enough. We also include parameters that are drastically important for the pharmacokinetics of some drugs, such as the hematocrit. And you can see how the hematocrit evolves as a function as the pregnancy evolves until reaching a value at delivery that is close to the adult's value between 45 and 50%. The fetal GFR also actually develops as the kidney are developing, starting around 30 weeks where we have detectable values, and then the GFR fraction increase until delivery. And finally, for plasma protein binding, we account both albumin and the alpha-1 acid-glycoprotein, where this time the amount is expressed as a percentage of adult level. And what we do, we pull both informations to estimate the protein binding in the fetal tissues. So we have a PBPK model for the maternal side that will change as a function of time, within the 9 months of the pregnancy. We have a fetal PBPK model, which has a simplified structure. I should have specified that. We only consider one fetal compartment to describe the fetus among all of the pregnancy. We don't describe yet all of the fetal tissues, such as the fetal kidney, the fetal liver, fetal heart, and so on, simply because data are very limited. And PBPK model is dependent on published information and published physiological parameters, and those are not really present out there to be able to create a fully validated and fully accurate PBPK model for the fetus side. So we are working on those currently, and we hope in the future we shall be able to have a fully PBPK models also from the fetus side. But as I've mentioned, the most important is really how the drug is exchanged between the maternal and the fetus. And for those, there are 4 particular pathways that the drug can use. But those pathways are not constant, and some of them will be major during the first part of the pregnancy, and some will take the lead during the second part of the pregnancy. So let's go over them. The first one is the intramembranous pathway. And this one defines the movement of water and solute being the drugs, that occurs between the amniotic fluid and the fetal blood within the placenta and the membranes. So this one basically defines how the drugs can go through the skin of the fetus before it is keratinized, so by simple diffusions. This pathway totally disappears around the 20th gestational age week, simply because due to the skin keratinization, the drug cannot permeate anymore. The second pathway is the movement of water and solute between the amniotic fluid and the maternal blood within the wall of the uterus. And this one is entitled the transmembranous pathway. So you have to see those two in combinations. First of all, the drug can exchange between the wall of the uterus and the amniotic fluid, and then from the amniotic fluid into the fetal blood through the skin in development. So those really are important during the early gestations. Finally, we have the fetal pathway, which is the movement of water and solute between amniotic fluid and the fetal organs. So the fetus will swallow some amniotic fluid. It will also secrete some residue into the amniotic fluid. So there is an exchange of drugs between those mechanisms. And finally, which is the most predominant pathway during the second and third trimesters, once the placenta is actually developed, is the transplacental pathway. And you have here the representation of a perfusion limited placenta as it will be used by default in the software. So we have four spaces, four compartments, the fetal blood, the maternal blood, and between those two blood compartments, we have the fetal placenta compartment. Below the maternal blood, there is the maternal placenta. So that structure mimics what is the real or close to the real physiological placenta structures. So those are for the exchanges between the maternal and the fetal. Oops. So in GastroPlus, what does it mean exactly? To set up the pregnancy model, and you will see that in a minute when I run the quick demo in GastroPlus, it is very simple. You just need to refer a few parameters, and you will be able to simulate the PK in a pregnant subject. Based on the gestational age, that is entered right there, if you're below 8, we don't account yet for all of the fetus structures because they're not really developed just yet. But we already account for the maternal changes linked to pregnancy by defining the weight, the total weight, and the weight gain. The differences will give you the weight before pregnancy, and this weight before pregnancy will actually be used to create the physiology of your mom, or of your virtual mom. Once we are after the 9th week of pregnancy, now you can see a lot of organs happening here, which are the placenta maternal, the fetal placenta, and the amniotic fluid compartments. So after the 9 week, if I go back to the structure that I've shown you, the fetal part will be created in the model. And once again, we enter the age of the subjects, the weight gain, and that helps us to calculate and create the physiology for those specific subjects. So Jasmine, I'd like you to launch the last pool questions before I go to GastroPlus. Thank you, Jasmine. So welcome to the 6% of experts. Thank you and welcome to the team. But I see that most of you have very little experience in GastroPlus. So sorry again for the experts. You will know what I'm talking about in the next few minutes. But I'd like to bring GastroPlus to the screen. So this is the GastroPlus software. And Jasmine, can you please confirm that you can see it?
Yes, I can see it.
Thank you very much. I appreciate it. So this is GastroPlus. So GastroPlus is a PBPK software that in some ways, all of the equations are coded for you. And you just need to put the right parameters to perform the simulations. It is divided in 5 windows or tabs. The compound tab, where we put all of the drug physical properties, such as the log P, the solubility, and the permeability. And those are important to assess the drug absorption, distribution, and so on. Then we have the gut physiology tab, where we have the ACAT model for the absorption of the drug in the gut. And you can see all of the parameters for the different segments of the GI tract. So with the local pH, the local transit time, radius, etc., etc. So the ACAT model is well known for biopharmaceutical application, such as formulation optimization, formulation development, bioequivalence studies, etc., etc. On the pharmacokinetic tab, and this is where we will play a lot today to create the PBPK models for pregnancy. This is where we can set up the kind of model we want to use, update the PBPK models if needed, and we can also enter a few more information regarding blood to plasma ratio or plasma FUP. And finally, in the simulation tab, this is where we can define the kind of simulations we want to run, the simulation length, and in the graph, where we will have all our results. So that was the ABC of GastroPlus. Now, the way we like to do like kind of gold standard to create a model in GastroPlus is first to import the structure using the ADMET predictor modules. And that module will estimate all of the physical properties of the drug and also provide estimates of blood to plasma ratio, of some metabolic enzymes, Vmax and Km, and maybe some transporters as well. And that can give us an indication of where is the, like what kind of drug we are dealing with, how it's going to be absorbed, and so on. So this is what was done here. We are talking about drug named cefazolin. Cefazolin is an antibiotic that can be used during pregnancy and is typically used before delivery to prevent any infection that could happen during the delivery process. It's typically administered as IV. So you will see here as I click, there will be all of the records that I have. So each record represents a specific study or specific simulations that we have set up. After we load the structure of the drug, and we have all of the parameters estimated by ADMET predictor, if we have some measured properties in vitro, we can use them and replace them in the model. And therefore, it will build confidence into the simulations. And then finally, I'm going to the third record. And in this one, I want to describe data for 1 gram administrations as an IV bolus in healthy subjects. I have already loaded my data and they are in the support files. And to do so, I would go to File, Load, IPD. And I got those data directly from a publication and I copy paste them using Excel. The model is set up such as we have a PBPK models right there. And the way we set up the clearance, it was because we want the clearance to be scaled between non-pregnant and pregnant subjects, we have to use a mechanistic clearance. We cannot just use a simple linear value because that would not be scaled. So we use enzymes and transporters actually based on publications. So if I click on transporter tables, there are 2 transporters, one influx O83 and one efflux MRP4 that are set up in the model and especially in the kidney. The KM were fixed based on literature information, and the Vmax were actually fitted based on data we had for 1 gram, but we had actually 4 data sets going from 1 to 4 grams, and we used those 4 data sets to fix and fit both Vmax parameters. So I will close this. So just to show you how the baseline model is working, I'm launching the simulation. I will show you the results. Here, the goal is to develop the model in the healthy populations. So we don't consider any pregnancy changes or anything. And as I go to new plot, you can see that the model is doing a reasonable job at describing the observed data. I will put it in log scale. We are doing a reasonable job at the beginning, kind of under predicting here, but there is an explication is because the linear binding, the protein binding is not linear for this drug. So that could explain the small differences right there. But overall, the shape of the profile is relatively well described. I'm not going to show you today the simulations for the 2, 3, and 4 grams. They are present in the publication we had for this case study, but they were also in a reasonable range. What I'd like to show you though is to somewhat confirm the Vmax or well captured is how we are describing the urinary data in light blue. And you can see the urinary secretion is overall well described as well by the model. There is quite a lot of variability, which was expected for this drug because cefazolin is both filtrated and secreted, so variability was expected. But overall, the model is doing a reasonable job. So now that we have that, what I want to do, I want to see whether or not my model can describe data not directly in the pregnant population, but in a postpartum populations. So after a few months after delivery in the same subjects, just to see if I need to make any model adjustment or not. So I will close this. And what I'm going to do, I'll go to database, copy drug record, and I have some help on the side to give it the name I want, and I'm not copying the support files. So I have a new record that will be created. And for this new record, I already have my data loaded right there. I need to change the dose to match the clinical trial I had. So it was a 500 milligram dose. I also need to create a new PBPK models because those subjects were different. So let's do a new PBPK model. The postpartum population was female. The age was 25 years old in the study, and a body weight of 62. As you can see, every time I'm changing parameters, the specific parameters for the tissues and the volume and the perfusions are also changing. Because based on the age and the body weight, the new physiology will be created. So I can click on OK and save that file. Then I can run the simulation. So for the AUC, it's well predicted. And if we look at the graph, we are describing the observed data once again really well for this compound. So that means that based on the postpartum information, I don't need to make an adjustment in this case. I can use the model directly to predict the PK in my pregnant populations. So let's do that. I'm simply copying my drug record once again, give it a name. And this time, I don't need to change the dose. Those will be the same. What I need to change now is my PBPK models because I want it to account for the pregnancy. So I can go to new PBPK. Once again, female population, but in the health status, I will not keep healthy, but I will go to pregnant. The age of my subject is still 25 years old, so that doesn't change. But this time they are pregnant. So I need to define the gestation age, and it is 25 as well, based on the study from which we extracted the data. The weight is 68 kilograms. And if you recall in the previous analysis, the weight was 62. So the weight gain here should not be 8.6 as we have here, but it should be roughly 6 kilograms. So my physiology had been created from the maternal side and also from the placenta and the fetal side. And I will save this model again. And I'm running the simulation. So once again, looking at the AUC, we have a pretty good predictions. And the observed data, this time in a pregnant population from the maternal side, are also really well predicted. So what does it tell us at this stage? We have a model in which we're able to predict really well the maternal differences, PK differences in one study. When we did that effort in the publications, we had more than one study, and I would once again invite you to read it to get more details. But I want to do one last simulation, this time for another study, but not at 25 GA, but at 39 GA. So I'll go to database once again, copy drug record, and this time, it's not directly a bolus, it's an infusion. The dose is 1 gram or 1000 milligram, and infusion time is really short, only 3 minutes or 0.05 hours. New study means a new population, which means I need to create a new PBPK models to describe this new population or these new representative subjects of the population. So let's go to new PBPK. I still have a pregnant female, so I can keep that. My age is now 33. My GA is right before delivery, so around the 39th week. And my body weight in that study was 79 kilograms. We didn't have in that study the weight before pregnancy. So I will go with the default for the weight gain of 15.4 kilograms. I can click on OK and save. And you can see how simple it is to create a new physiology for pregnant subjects. Once you have your model validated with the right parameters in the right sections for your healthy subjects, you can do a lot of simulations for the pregnancy side. So let's do the simulation and let's see where we are. So from the Cmax, we are right on point. For the AUC, we are not too bad. And from the maternal side, you can see that the model overall, I put it in linear scale, is able to describe the data. There are quite a lot of variability, but we are around the middle all the time. The idea would be to run a population study to see whether or not we're able to capture the observed variability. We don't have time to do that today, but it could be an option to double check. What I want to do now is not to look just at the maternal side, but I want to look at the fetal side. So I can go on new plot and then select curves in the pharmacokinetic tab, scroll down. So once again, with time, you get used to it. and select the fetal venous returns, because in that study we had those kinds of data. And you can see that as an initial predictions, we are in the right log, which is already good enough, because if we didn't have any clinical information, we'd not be too far from the study. However, it seems the dynamic of the absorption for this compound is not perfect. So let's go back to my PBPK model and let's see if we can adjust it. So we will go to Edit PBPK. And what I want to do, because you can see here the whole structure of the model, instead of using a perfusion limited placenta, I will use a permeability limited placenta. So I can make a right click, change the tissue model, and go from perfusion to permeability. They will turn green, which means now I have this permeability model. I want to account for the differences in surface area between both tissues. So I want to account for the specific, using the specific PCC parameters that will give me this parameter that accounts for the permeability between the extracellular and intracellular space of the placenta. So I will cheat slightly simply by unchecking and checking it and use the value I have already entered. So it gives me a PSTC of 75.85 for the maternal placenta and 1/10 to the power of 5 for the fetal placenta. So I can close this. And I will run the simulation again. So you can see that from the maternal side, it didn't change much. My Cmax went from 139 to 140, so it's pretty much the same. And my AUC is also pretty much the same. It was around 150 as well. So from the maternal side, everything is pretty much the same. But now, and I make that bigger, if I go to the fetal venous return, and I simply ask him to refresh the curve, the dynamic of the exchange between the maternal and the fetal has changed drastically, and we're able to describe the data relatively well. So that is what I wanted to show you in GastroPlus. And if you have more questions, we can always take them after. I'd like to go back to the slides for the next few minutes to show you a couple of more case studies that we had. And the third case study, which is pretty similar to what we've run, is for API that are eliminated solely by the kidney. So cefazolin was one. The other one is cefuroxime. The modeling strategy is always the same. We want to develop and validate the model in the healthy population. Then, if needed, there is a gap or a step that can be done is to make some model adjustments for using the postpartum data. Of course, if we have them. And finally, with the refined model, make the pregnancy predictions. So this is what we've done for the cefazolin, but we didn't have to make any adjustment using postpartum data. So for cefuroxime, here you have the model validation, knowing cefuroxime is also cleared by the same mechanism, so by renal filtration and active secretions. The same transporter OAT3 and MRP4 are involved, and once again, the Vmax were fitted for this compound. We have all tissue defined as perfusion limited, except for the kidney that was permeability limited, and I could have precised that in the previous one. We need to have permeability limited tissue for the kidney to be account for both influx and efflux transporters in the kidney. In the end, for cefuroxime, the PBPK model could relatively well describe the observed concentration following the IV administration at 3 doses which were 0.25, 0.5, and 1 gram IV bottles. For the postpartum data, we had to make a small adjustment to the Vmax and reduce it by half in order to be able to describe the urinary secretions. So we reduced that Vmax by twofold, and then the urine secretion was well captured. And once we've made that change, actually, the PBPK model could reasonably describe both the IV data and also the urinary secretions. So we went a step ahead and wanted to be like perfect. Once we had that model adjusted, we could make a couple of simulations. And you can see here that the plasma at 18 GA, so just as an age, 41 GA from the maternal side in blue is really well described. And from the fetal side, both the fetal blood and the amniotic fluid concentrations are also really well described, and the dynamic is good. For the dynamic, as I've changed, we had to change also for this drug, the placenta model, to permeability limited. And one paper, if I recall, published in 2019, looked into the distribution of transporters in the placenta. And they identified that the MRP2, 3, and 4 are present on the apical membrane of the placenta from the maternal blood, and they may go against the diffusion of the drug from the maternal to the fetal blood. So here on the right-hand side, you have the structure of the permeability limited placenta model. And you can see those PSTC parameters right there are the ones that we optimized in the cefuzolin case and also in the cefuroxime. Those parameters were used as surrogate to the KM or Vmax parameters that we didn't have for these drugs. We had the KM parameters, we didn't have the Vmax, and also those transporters in gray are the ones that were detected in the placenta, but the expression level is still unknown. So we were not able to use the KM Vmax parameters for those specific transporters, but going from permeability, from perfusion to permeability limited, help us to capture the trend. So what it's telling us is for drugs where transporters are involved, potentially the placenta structures should be permeability limited. We had a few validation data sets, actually 3 of them at different doses from 750 milligrams to 1500 milligrams and different gestational age. And in all cases, both from the maternal plasma profiles and the fetal blood cord were all described relatively well. So I see time is running, so I will go slightly faster for the second case study to give some room to some questions. But it's for API eliminated solely by the liver. So we are currently working on these publications. But the drug I want to talk about is metronidazole, and we use the same modeling strategy: model development in healthy subjects, model adjustment in postpartum, and pregnancy predictions. Melatoninazole is a drug that is only metabolized by a couple of enzymes. We have the 3A4, the 2A6, the 2E1, and the UGT. In this model, all of the tissues were defined as perfusion limited. You can see how the IV and PO profiles, plasma profiles, are well described by the model. So we had our baseline model fully validated. And in the postpartum data, for both 0.25 and the 1 gram PO, this seems to be relatively well described. So we were very satisfied by the model, and we could move into the PK predictions. So first, from the maternal side, at 11 GA, we're able to describe those 0.25 and 1 gram relatively well, although we were slightly over-predicting right there, probably due to the disappearance of some subjects between the pregnancy and the postpartum group. So that would be to double check really if we had individual subjects data. Another study looked into the PK of this compound at 12, 24, and 36 weeks of pregnancy. And in the 3 cases, overall, after multiple administration, the model was able to predict the PK relatively well. And finally, as a model validation, we had once again 3 studies with both maternal and fetal data. And the data from the maternal sides are always really well predicted. For the fetal blood, we are also doing once again a great job at describing the data. And then for fetal or placenta concentrations, knowing it was very early in the pregnancy, we are doing a good enough job, I would say, in terms that we're in the right ballpark. You can see here that we are slightly overestimating both fetal and placenta, but it's also the case for the maternal PK. So probably if the maternal were lower, the fetal predictions would be lower as well. For this study where the plasma PK in the maternal side is perfectly described, we are on the right range for the placenta, which is also encouraging. And for the fetal, we have only like a few samples. So it's hard to have a hard conclusions yet on the ability to predict the fetal concentrations. However, we are definitely in the right log and the right ballpark. So that's interesting to know compared to having no informations. So as a quick summary, we have ethics and safety concerns for pregnancy population studies, clinical studies. Pregnancy PPK models, they can predict both the maternal and the fetal PK/exposures. Postpartum data, they may be interesting to calibrate the PPK models. As you've seen during the 3 case studies, we actually used them once to set up the model. There were other cases that we run that I haven't talked about where we use them once again. So far it's a 50-50 where postpartum data were necessary to adjust the model. And the placenta model structures, I haven't specified the metronidazole, but we kept the perfusion limited placenta and it worked well on its own. So probably based on the mechanisms involved in the clearance or distribution of the molecule of interest, the placenta structure would have to be adjusted, knowing that if we have transporters, potentially using a permeability limited model would make more sense. So to learn more, I would like to invite you to read the publications we had on this project that was published earlier this year. And I'd like to acknowledge Dr. Tseko, Dr. Dupont, Dr. Zhu, Dr. Lukakova, and Dr. Bolger for their collaboration in this project that we started 4 years ago. And we are very proud to show you the results today. So with that, thank you very much for joining, and that leaves us only 5 minutes for some questions. Thank you very much.
Great, thank you, Maxime. So we'll start with the first question, which is, are pregnancy PBPK model applications limited to pharmaceutical drugs? And what is needed for the next steps?
Thank you very much. So that's actually a good question. And the answer is no. Because in PBPK models, we looked into the physical property of the drug, and we can predict some of those. As long as we have the chemical structure of a molecule, whether it's a chemicals, a toxin, or any drugs, we shall be able to make predictions. Then the value of the predictions will be dependent on which data we have to validate the model. But if we just have the structures, we can start to make previous simulations and directions into where the drug, or if a drug or a chemical entity would permeate the placenta and by how much. For the next steps, I think I've already touched base on that in one of the slides. The next steps would be to develop the fetal full PBPK models. There were recent publications published in 2015 on that that describes full PBPK model structures, but the limitation is first of all, we don't have all of the relationships just yet for all of the tissues. I mean, they exist, but they are not all fully validated. And the second point is about validating such a model, because we may have data in the fetal blood cord. So that was the green one I was showing that we are able to capture really well. But then it would be purely simulations and hard to validate. So later on for applications, it may become an issue. Next question.
Okay. The next question is, can you consider amniotic fluid in the PBPK model?
Yes, it is. And sorry, I realized I went fairly fast on that. So let me go back. Oops. Let me go back to the structure right here. And we have actually the amniotic fluid compartments here. And the volume of the amniotic fluid is also set up and regulated as a function of time and during the pregnancy by all of those pathways right there, except the fourth one, obviously. But the volume is regulated, and we have a relationship that double check. So the volume increase during the zero, not the zero, but during pregnancy, and it decreased towards the end of pregnancy. So yes, we have these compartments, and actually, in one of the case studies, which was the Cefusol, this one, sorry, here you can see the prediction of the concentration in the amniotic fluid.
Awesome. So the next question is, can GastroPlus capture differences in fetus plasma concentrations if you change the fetus gender?
Yes, yes. So if I go back here and create a new PBPK, you can see you have the fetus gender parameters between male and female. So as we change those, you can see those parameters have changed slightly. So you can make predictions for both a male and female fetus.
With that being said, can we also predict fetal to maternal transport?
So all of the transport is going both directions, mostly based on the diffusion Fick's law. So it will go in both directions. I don't think at this stage we would be able to do a simulations for fetal injections and then look at the maternal exposure. I don't think that has been set up because, and I'm not an expert in that, but I would think that's pretty rare. But that's something we could discuss in the future to set up.
Okay, thank you. So another question is, do we need to run ADMET predictor before entering the chemical structure?
So it's actually both. You're actually using it at the same time. You import the structure in GastroPlus, and it will be read by ADMET predictor, and that then will populate GastroPlus with all of the chemical structures. So it's a two-in-one process.
Okay, and I think I have one more question here. And I think you answered this already, but does GastroPlus have pre-built PBPK models with all parameters defined?
So we don't have that as such, but you can see our website information here on our emails. I will invite you to reach out to us, because if it's a model we've published on, we could potentially be able to share some files or discuss about it. So it will be a case-by-case scenario. So if you have a specific drug you have in mind, I will invite you to reach out to us, or you can reach out to me. You simply need to replace info by Maxime and then add simulation-plus.com. And you can ask the questions, and then we can discuss further.
Okay, thank you, Maxime. We invite our audience to learn more about GastroPlus on our website, like Maxime had mentioned, at www.simulations-plus.com. You can also find some of our other team members at this year's AAPS meeting, which is next month. This webinar has been recorded for playback and will be available on our website and YouTube channel. This concludes our webinar for today. Thank you so much. I hope everyone has a good day.
Thank you, Jasmine, and thank you all.